Okay. Okay. Good. And thank you, Kai, and for giving me this opportunity to share and what has been done in the power quality field. I felt that some information could be useful for this group. So so the main purpose for this is to share experiences on disturbance location from power quality perspective. I hope you can stimulate more new ideas for oscillation source location. I will talk about 4 items. First is give you background information on key power quality disturbances and why we need a source location. This will be very brief. Then I will discuss 2 problems and we faced in the past. One is, the problem and the solutions. Then I will spend more time to talk about a real life case on locating voltage flicker source. This voltage flicker can be considered as a form of oscillation. Okay, so finally, I will summarize to discuss with you what kind of useful information can we extract from this PQ activities or the experience done in the field of PQ. Okay, so and if you have any questions or I lost any connection or things, please feel free to interrupt me, yeah. So basically, let's start. So power quality is concerned with impact of disturbances on utility customers. Okay, so that is the main focus. There are 2 types of disturbances. One type is transient disturbances, one type is steady state or sustained disturbances. Transient disturbances, for example, like surges, like capacitor switching surge, which is formerly called voltage transients, and also voltage dips due to sag, due to fault. So you have one phase, in case 2-phase fault. So you have voltage sags or voltage dips. Yeah. And those are come and go. Those are called transient disturbances. There are other type of disturbances called steady state disturbances, which is sustained, like harmonics, voltage unbalance, and voltage flicker. This is the waveform, top part of the waveform of voltage flicker. Each spike is 1 cycle. So I have to condense them so you can see the flicker pattern, right? Okay. Personally, I think power system oscillation are essentially a type of electrical disturbances. Since the main victim is power systems, so it has been not labeled as a PQ concern. Okay, so that's the administrative distinction, not a scientific distinction. Yeah, from my perspective. Now, and why do we need to find source locations for power quality disturbances? There are 2 reasons. Let's look. The typical arrangement is this: we have a utility system, we have customer facility. There is a point of common coupling or metering point here. If there is a damage to the customer equipment, the question is who is responsible for that? We need to know if the disturbance causing damage coming from a utility system or from the customer facility itself. So it's very important to know whether this particular damaging disturbance coming from upstream or downstream. Another is that if the power quality limit is exceeded, like a harmonic limit, say, suppose limit is 5%, we measure the 7% limit. Then we go, utility means goes to the customer. Hey, you fix the problem. But the customer say, hey, because you increased the voltage distortion at this location by 3%, my contribution is only 4%. So I'm not going to fix that. The question becomes, who is responsible for the excessive harmonic limits at the point of common coupling exceeded the limit? Okay. So those are 2 types of responsibilities we need to determine. So, and as a result, there are 2 types of source location problems. One is qualitative, means yes or no. This is for transient disturbance. Is the disturbance coming from the utility or from the customer? By the way, can you see my mouse?
Yes, we
yes,
can.
Hello. Yeah, okay, good. Yeah, another one is quantitatively, which means how much for steady state disturbances. So what is utility system contribution to the limit violation? In this case, we have to isolate utility systems contributions. Okay, so that is the need why we need this disturbance source location and solve this problem. Now, what is the infrastructure available for the monitoring? Okay, so the disturbance monitors and are widely deployed these days. Power quality monitors, basically PCC points of our transmission connected customers, as shown here. Okay, those are the monitor points. Then PCC points of many distribution connected industrial customers are also monitored. Then PCC points of our generators sending power to the grid. So basically our generators, transmission distribution are monitored. I highlighted this is blue because oscillation sources sometimes are related to generators. Now sending end of primary of many distribution feeders in a substation. Basically like this is a substation. You have multiple feeders. Now every feeder is monitored. Okay, so that is the current state of monitoring in developed countries. Okay. Now, and the capabilities of current disturbance monitors are the following. First is the voltage current waveforms of transient disturbances captured. If you have a transient disturbances, it automatically capture. Typical going sampling rate now is 120 samples per cycle. So, and in power quality, we like use how many samples per cycle instead of sampling rate to discuss. That give us an idea how many harmonics this can be analyzed. Okay. So another one is the voltage for steady state disturbances is the voltage and the current waveform snapshots and the indices such as the harmonic voltage level, negative sequence current, etc. So this snapshots taken, for example, could be user can set one set output for 15 minutes. You can set a more frequent reporting, but that means you have more data to store, right? Typically is 10 minutes or 1 hour, one reporting. For one reporting, there's one data point coming out, could including 12 cycles of waveform and its spectrum result, okay? So the recent development is continuous non-gap waveform recording. Means just record everything, regardless, okay? So, and nowadays, the highest recording now you can go with 128 samples, 6 channels, 6 voltage, 6 current, record for 6 months, non-stop, okay? That's the latest development. This is very much mimic the security camera recording progress. You can think of this as a security camera recording. In the traditional security camera recording is that you record one using motion detector to detect an event, then you record, right? If there is no motion detector recording, you're just taking snapshots of the area you're monitoring. The recent development is that we just record everything. And in case there's some security event, you can always go back to analyze. The power quality trend is similar. So the data, where the data is stored, data are normally stored locally in the monitors, and it can be downloaded on demand. Monitors means the monitor in the substation. The utility has a very good connection to the substation equipment. They can download anytime, high-speed download. Pretty much like a Netflix type of streaming download. Okay. Now, and the data are stamped. 2 types of stamps. One is GPS clock, or your monitor's internal clock. This is not accurate. It's good to know which minute, which day you record the data. But a GPS clock synchronization means can synchronize every data point. If you have 2 locations, like for example, you record here and here, you have 2 waveforms. you have to line up those two waveforms properly with the same time. Then GPS timestamp can be used to line up them. Okay. And nowadays, increasingly more monitors have the GPS clock to the monitor. Okay. So that's the infrastructure. Now, how this thing operates in terms of the mode of operation. From power quality management perspective, there is no need for real-time or your online disturbance source location, because once you have the disturbance, protection is the first line of defense. You trip regardless of where the location is. And as a result, location information is not needed to trigger immediate action, even though some location information is available immediately. I will show you the algorithms. Okay. Now, and the location information is used mainly for post-mortem analysis, such as troubleshooting and the dispute resolution. Okay. So this task is normally done offline by PQ engineers. Some monitors provide a qualitative location information already. You don't need the analysis. You just download the monitor information, it will show transient disturbance is coming from downstream or your upstream. Yeah. So in some cases, multi-location monitor data are utilized to reach a conclusion when multi-sources are suspected. For example, you have a ski resort. This is actually happened in the Banff mountain. Okay, we have been asked which resort is causing problem. So we have to analyze 3 locations simultaneously to determine the responsibility of each location. Okay, so that's basically give you our background on power quality monitoring and the need for source location. Now I'm going to show you 2 source location problems and their solutions. One is locating sources of voltage transients and the sags. So the monitoring location is at the PCC point of the interface point. The form of the results is qualitative, means that if the disturbance is from utility side or from the customer side. The application studies, actually some power quality monitors has implemented one of the 2 methods. Okay, so let's talk about it. The first method is disturbance power and energy-based method. It's very intuitive. Okay, and so basically imagine this is a customer facility. This is utility system. You have a capacitor switching event. You energize the capacitor. Of course, there is the energy needs to use to charge the capacitor. Some energy could come from the customer side. Some energy could from utility side. Anyway, at this PCC point, it's likely the energy will flow this way. Therefore, by the direction of the power flow, the transient power flow indicate the location. The data and the waveform data is needed because this is the transient event. You want to find the disturbance power. Power or energy. Energy means integration of power to get a result. This is one way. Another way is that use impedance estimation based method. The idea is this. Again, you have a disturbance here. You do switching here. Now this switching can be used as a kind of a test signal for you to estimate the impedance on this side, on the right-hand side. This right-hand side, in this case, is the customer. There is a voltage change, there is a current change. You can estimate the impedance of this change. Then the sign of the real part of the impedance or the reactive part of the impedance can indicate. I mean, talk about the low frequency impedance at 60 Hertz or some other low frequencies below, say, 300 Hertz. From this impedance, the sign, you can tell if the disturbance coming from this side or this side. If the disturbance coming from this side, that means the impedance estimated is from the utility impedance. Then you can also, based on the polarity of the connection, you can know the sign of R or X can indicate the location of impedance. This is very similar to distance protection. Distance protection has in the room or the opposite side of the room. Just a similar principle. The only difference is that this is the transient impedance. You need to use transients to estimate the impedance. Again, waveform is needed for the data estimation. So those have been maturely developed. Some monitors have been implemented such methods. Now, how about a steady state disturbance? Like I say, determine the respective contribution for harmonic voltage at the PCC. Okay. Again, the metering point is the interface point. The results has to be quantitative. For example, what is the harmonic contribution of customer at the PCC? Application studies, unfortunately, this problem is still unsolved. I have been researching this for more than 25 years, and we still couldn't find a solution which convinces everybody. Okay, let me explain the challenges, why this cannot be done, even for today's technology. Okay, basically, both sides contain harmonic sources. Customer obviously has harmonic sources. That's why you are monitoring. Utility side has harmonic sources too, because they have other customers connected. This will be the equivalent source from other customers. Now, and therefore, both sides can be represented as a Norton circuits. So basically, VCC is caused, the harmonics at this point is caused by both customer harmonic source, utility harmonic source. Thus, the task is to determine the respective contribution of IC and IU at this point. Okay. The problem can be solved in theory using the principle of superposition. It's very simple. Superposition, you see, you find the contribution from this by assuming this is zero, then contribution of this by assuming this is zero. You can do that. This is in theory, but in practical implementation, it's very difficult because we have to estimate all four quantities simultaneously at any instant, okay? But we need the disturbances to estimate, but disturbances don't happen all the time, okay? So as a result, that is not standard method. So original motivation to do this is that ideally, assuming you have such a method, you can implement in this meter, just like a power factor meter, you can charge a customer when they exceed the limit, just like a power factor charge. If this can be done, the power quality management becomes automatic. You don't have to tell customer what to do. They automatically will do it because to reduce the cost of a bill, right? So this problem hasn't been solved. So the only way you can do that is use statistical correlation of a long period, often used to determine responsibility in practice. So that means case-by-case solution, like a 3-ski resort case, we have to use a statistical correlation to do that. That is one thing important to clarify. The energy power-based method does not work in this case, even qualitatively, okay? This is a very complex explanation. I'm not going to spend the time to explain this here. But this has been proven doesn't work, okay? To detect the harmonic sources, or which side is larger harmonic source, okay? Okay, now this is 2 examples. Now I'm going to talk to you a real life example about a forced oscillation voltage flicker caused by variable frequency drives. I'm going to go to a little bit more detail here. So basically, here is a distribution system, and which is supplying a pumping station here. Okay, this pumping station has a 3 MVA drive. Okay, so over the years, there is complaining customer C, especially, which is a school, complaining lighter flicker. Okay, this is the town also sometimes reported that too. The utility spent years, at least 5 years, couldn't figure out the problem. Then no, this is related to, from anecdotal evidence, is related to the operation of this pumping station. But the pumping station owner, which is a multi-international company, okay, said, hey, my load is steady. I'm just pumping liquid oil. Okay, I don't have fluctuating load. How can I create a fluctuating voltage? Okay, you need a fluctuating voltage to cause light flicker, right? That is, everybody agrees that is the case. Then how could there something fluctuating? So when I approached my group, and then I always puzzled why this is the case. But immediate solution is let's monitor the waveform, multi-cycle waveform to see what happened to the waveform. The waveform must demonstrate some fluctuation, okay, in order for light to flick, right? Okay, so we monitor the 4 seconds waveform. This is one example here. Okay, you can see that there is a fluctuation of the magnitude here. Now, the question is, why the magnitude fluctuate? So obvious, the first step is to do spectrum analysis, right? So here is the spectrum analysis. We found, you see, these are the harmonic components here. We found that interharmonic components here, there are lots of spectral components. This is the enlarged portion here. You see that? This here is the enlarged portion. This is the 4th order harmonic, is actually in this bin. But the rest is actually interharmonics here, okay? What is interharmonic? Interharmonics are spectral components whose frequencies are not integer multiple of fundamental frequency. So when you divide the frequency, they're not integer, okay? So, and now basically, clearly interharmonic is the cause of the fluctuation, okay? Now, and otherwise, how can you explain this, right? Because interharmonic, this is the frequency domain representation of the oscillation, right? So now we dig into the problem, find the explanation is very simple. Why interharmonic cause fluctuation, okay, or oscillation? Let's just look at a simple case, a 60 Hertz wave, add an interharmonic component. Okay, the magnitude is 30%, just shown here. There is this is interharmonic frequency. In this particular case, I show the interharmonic frequency as 1.1 or 0.9 harmonic. Okay, so and now you can see that the interharmonic. This is the fundamental frequency wave. This is the interharmonic wave. Interharmonic by the nature, because this interharmonic, the peaks are not synchronized with the peak of 60 Hertz wave. When you add these two together, in this case, the peak cancel out each other. Then in this case, the peak added together. Therefore, when you do the phasor calculation, use this PMU equation. Okay, phasor is essentially to the RMS value of this wave, which is proportional to RMS value of this frame, or your RMS value of this frame. That's why I got one dot. For one 60 Hertz cycle, another dot. This is the phasor result. Phasor result only give you one dot per cycle. So you can see that A obviously has a low magnitude because they cancel each other. The B has a higher magnitude because they add. So that explains why the interharmonic cause oscillation. Okay, phasor oscillation. Interharmonic cause phasor oscillation. Now the question is where the interharmonics come from. Okay, so the drive, just we know how variable frequency drive produce harmonics. Never heard of variable speed drive produce interharmonics or interharmonics from somewhere, right? In fact, we did research on this, also did the literatures, okay? So, and I mean, the first step is find the source before we draw a conclusion, see if the drive cause harmonics or interharmonics or not. The idea is very simple. Where the interharmonic comes from, extremely rare. There are multiple sources in the grid that produce exactly same interharmonic frequencies. Therefore, it's logical to conclude there is only one source producing this interharmonics. This source must inject interharmonic power into the grid to cause flicker, to make the voltage make the interharmonic voltage flow, it needs power. Okay, therefore the direction of interharmonic power can be used to locate interharmonic or flicker source. This is what we did. We basically, the monitor is the interface point. This is the plant, pumping station plant. We monitor at the point. Then we computed the 60 Hertz power, which is a positive, means going to the plant. We computed interharmonic power, which is negative. Clearly, this shows the plant is the source of interharmonic. Okay. Okay. By this time, we know the plant is source of interharmonic, but it's not enough to convince the pipeline company, because they will say how and we know our drive produce harmonics. We add a filter here to mitigate harmonics. What is interharmonics anyway? And why it's coming from our drive? Then we did an investigation. We researched the research on drive and also did our own research and found VFD does produce interharmonics in theory. Okay, it's very small. That's why people don't pay attention to that. Okay, interestingly, these interharmonic frequencies are related to the motor drive speed. So basically, that is a function you can derive mathematically. Interharmonic frequency is a function of the drive that produce two key interharmonics. Okay, so it correlates, our measurement correlated this very well. So this correlation basically confirmed that the VFD is indeed the source of flicker. So basically, we use this two evidence presented to the pipeline company. That basically the back off. Okay, so they have accepted. That's the problem. Then they invited the drive manufacturer come over to solve the problem. And we had a brainstorm session. Then we figured out a way, a novel reconfigurable harmonic filter for the plant. The problem caused is by this. Okay, so basically interharmonic is a current being injected by the drive. This is the filter. This is the system has an impedance. Imagine the filter as a capacitor, system impedance as a reactor. That's forming a parallel resonance point. As a result, at around 240 Hertz, you see here, there is a large increase of interharmonic voltage, which causes voltage flicker. Mainly this component, not this, okay? So to mitigate this resonance is actually very difficult. The reason is that the interharmonic frequency changes with the drive speed, okay? Harmonic frequency is fixed, the level change, but the interharmonic frequency changes. So you always hit a resonance. Then the idea we developed is a novel reconfigurable harmonic filter for the plant. It solves the problem. Since then, the drive manufacturer, which also provide a filter, applied all this to the pipeline users. If such a problem happens, they use this approach to solve that. Okay. So basically, that's what we learned from power quality investigation. Now, I want to discuss with you, because most of you work in the phasor domain, an important question is, can we solve this flicker source location problem using dynamic phasors? Okay, I will, answer this question, use two examples. Okay, one is theoretical perspective. That's a circuit. Let's just study this simple circuit. So we have, it's a 60 Hertz impedance. We have a voltage source, which is dynamically changing, basically has an oscillating magnitude. Let's say, just pick a number, say 20 Hertz oscillation. So the source can be modeled as a dynamic phasor in this form. One is 1 per unit. The 1 per unit oscillate 10%. Okay, so how do we solve the phasor current? Okay, so and the standard method, obvious, we learned from a circuit, is E divided by the impedance. Then you get the phasor current, which is a dynamic phasor. Now I want to pause here. Let's discuss if this solution makes sense. Can any of you share this? Because this is a question I asked people, including myself before, I thought this is obvious, right? Do you?
I think this is
can
not
you
correct because the impedance is defined based on certain frequency. Now the frequency is oscillating, so the impedance will change. So this formula is approximate, but it's not accurate.
Yeah, exactly. Because this is 60 hertz. This is changed to 20 hertz on top of the 60 hertz. Now, what is the frequency? Okay, right? So the correct solution is the following. Okay, actual voltage is equal to the magnitude times the underlying 60 hertz component. When you multiply them together, you get a fundamental frequency component and the two interharmonic components. Okay, look, this interharmonic components or fundamental frequency component has constant magnitude. So therefore, there are three static phasors. Then we can use the phasor analyze calculation for three sources. There's three sources here, which each has a different frequency. The math will show one interharmonic has 80 hertz, another interharmonic is 60 hertz. Therefore, the correct way to solve the problem is use the superposition method shown on the right. Okay. So I use the 40 hertz as an example. 40 hertz, this impedance is 0.66 per unit. This impedance is 0.6 per unit. They cancel out each other. By the way, when you do the 40 hertz calculation, I use this as scaling factor because reactor increase with frequency, decrease frequency, right? When frequency decreases, this is a decrease case. 40 hertz is decreased. So this is decreased. Capacitance impedance increased. So that happens add up equal to infinity. Therefore, the current, actual phasor current should be infinity in this case. Okay. So this shows that it is not possible to use a phasor to solve this problem. This is exactly what happened. In this VFD case, we have resonance at 236 hertz. Therefore, okay, then the dynamic phasor will not be able to work in this case. Now, another example I want to say is that practical perspective. The previous one is a theoretical perspective. Another perspective is the practical perspective. Let's measure, can we measure dynamic phasor properly? Let's assume we have a magnitude very dynamic phasor. In this time, I put 42 hertz here, the phasor model. So basically, this is the magnitude of phasor underlying 60 hertz wave. I multiply them together, becomes the actual waveform. Then I use PMU algorithm to compute, to measure the phasor. Okay, then I plot the original dynamic phasor on top of that. Now you can see that, okay, the PMU measurement or any phasor measurement technique will show this is the 80 hertz oscillation, but the actual dynamic phasor oscillates at 42 hertz. So why this is the case? Because according to Nyquist theorem, a phasor can only report up to 30 hertz oscillation frequency. If any oscillation frequency greater than 30 hertz, phasor result is corrupted by the aliasing effect. Okay. So, and that is so to summarize, from theoretical perspective, we cannot detect resonance using dynamic phasor. Then from practical perspective, we cannot get proper results to do analysis anyway. Okay, now let's do a demonstration to give people a feel what I'm talking about. Just a simple Excel demonstration. Impact of interharmonics, harmonics. Let's see what happened in the waveform. This one, we change the interharmonic frequency. This one is, let's change the oscillation frequency. Let's see what PMU will measure, okay? Let me turn on my Excel. Can you see this Excel now?
Yes.
Yeah, okay. So basically, I will share this Excel with everybody. This is to simulate these two waveforms added together. I just copied one case into my PPT. Okay, so this is the frequency you can change. This is the harmonic number, okay, not the actual frequency. For example, harmonic 1 is 60 hertz. So you can say this two add up equal to 63. This is slanted, it's because the scaling, okay? This is automatic scale, so this is not, doesn't mean the actual RMS value is changing, okay? So it's a numerical changing. So let's go for the harmonic, for example. You see, when you have a harmonic peaks and values are synchronized with each 60 hertz component. So the RMS value don't change. Again, the slope is caused by scaling. When you do the plotting, you can change the scale, okay? So, and I don't want to change the scale because when I do the interharmonics, this will vary a lot, okay? So that's 3.1 interharmonic. You see that, okay? You can see that interharmonic, because it's a high frequency, has harmonics. So, and it causes waveform modulation, like this. This is the modulation. Then also waveform distortion. So most interesting is the interharmonic around the 60 hertz point line. You see here, which is what we have seen, or 1.1, okay, which also have this. Now you can 1.5, okay. So, and now you can go say 5.5, you can still get a phase oscillation, but of course, this modulation is very hard to see, but you will see some, okay. Okay, so that is one demonstration. Another one is dynamic phasor demonstration. Dynamic phasor is, I put it here, this giving me, this is 0.7, okay, 42 hertz. That's the one we just plotted. Let's 0.1 hertz. You can see, very slow, like a synchronous machine. Oscillation, 6 hertz of oscillation. Even you can go even smaller, 0.01. You see the overlap, the oscillation is very slow, okay? Okay, so 0.1, you can see the phasor result, PMU and the phasor match very well in this case, low frequency, right? Okay, now if we go with 0.5, that's a boundary, 30 hertz. That's a boundary that already have some differences, okay? One difference is because the curve fitting, the blue curve I used the Excel scattered plot is the curve fitting here, okay? Now, if you go to say, on the 3.5 harmonic, the frequency goes high. You see, this phasor still, the true dynamic phasor still oscillating, but the PMU, because the aliasing, they're recorded as a constant. Okay, that basically exceeded the bandwidth. Okay, so basically that's the demonstration. You're free to try it out. So I'm going to share this with you too. Now, and let's come back to the presentation. Okay, that's basically my power quality presentation sharing with you. Now I just want to summarize and what I have talked about in terms of what can we learn. Should we the question is good for discussion. Should we reformulate the problem? Because forced oscillation is very likely associated with a single source. That's qualitative answer may be sufficient if the source is up and downstream of monitor, right? Therefore, independent monitors at the PCC points are sufficient, leading to simpler distributed source location scheme. We don't need a networked system to do that. That is now need for combined analysis. And from multi-location, since that is only one source to determine upstream or downstream, that's it. Yeah. Also, my feeling that this is not a real-time process. Of course, you are researching this, you know more, similar to PQ, because to use this to trigger protection, which will be a very conservative utility system, you need years of demonstration that it can detect sources properly. So probably initial process is offline or for monitoring that is now triggering. So it's a non-real-time process. That is how I think if we think it this way, we will make the problem simpler. The next question I like to discuss, should we consider alternative waveform-based data approaches? First is that waveform data are most authentic data is widely available nowadays. Those are some pictures of the waveform data monitors available. Like this portable, this waveform synchronize, this GPS signal you can synchronize. For example, in my lab, I have 3 of this going to the field to do measurements. Stationary PQ monitor, this is a gapless waveform monitor, can monitor 6 months non-stop. Okay, 120 samples per cycle. Relay-based, this is the merging unit for digital substation. In the future, everything coming in the digital form, waveform. Now this data circulated in the distribution Ethernet to be used by protection and other devices. So the default data in the future is waveform data. Okay, so and the waveform data can give interharmonic information. Now interharmonics are actually related to the modal frequency of the state equation. Of course, this EMT model-based state equation. They're the same thing. When you have a model frequency, then like an IVR, for example, when they do the studies that shows they have 80 hertz model unstable at 80 hertz, which means actually 80 hertz interharmonics. So IVR units plans can oscillate on the higher model, which interharmonic frequencies. Then PMU phasor has limited bandwidth due to next construct. So basically, that's what I want to discuss with you. Hopefully can stimulate more thinking. I have done some research on interharmonic-based method for forced and natural oscillation source location, including those involve synchronous generators. So if they're interested, I can share that in the TF meeting in the future meeting, near future meeting. Okay, that's basically it. Yeah. Okay. Yeah.